We're on chapter 4, kinematics. It's a fancy word for just motion without regard for its cause. We talk about forces that put things in motion. Well, we're not going to talk about those forces now. We're just talking about the motion itself. We'll start with just position. We have an x-axis labeled in meters. We can ask ourselves, where is that ball? We'd say the position is at -1 meters. The ball later is found at x equals 2 meters. We have an initial and a final position. What's the displacement? It's the change in position. That's the x final minus x initial. That would be 2 meters minus a -1 meter. And notice I'm using the units and the formula to show you what's going on. The displacement is 3 meters. Now that's for the ball going from this initial position to that final position. What if it went the other way? We'd have displacement again being x final minus x initial, and we'd have -1 minus 2, giving us a -3 meters. Well, this one's positive, that one's negative. That tells us something about displacement. It's a vector. We don't usually write the arrows on top of all these things every time. We just get used to knowing that it's a vector. So remember that displacement is the change in position. Now we move on to velocity. The ball is going to start at -1 meters at time 0. Imagine we see a ball moving to the right, and a camera is taking a picture of this once every second. The ball reaches 2 meters at t equals 6 seconds. What would this motion look like if we plotted it? At time 0, the position is -1 meters. That is the initial position. At time 1 second, we're at -0.5 meters. And this goes on until at 6 seconds, we reach 2 meters. We draw in a best fit straight line. How can we use this line to find how fast the ball is traveling? It's the slope. You want to know how fast you're going? The rate of travel is the velocity. That's the displacement over the time. Let's sub in some values. We have 3 meters divided by 6 seconds. The ball is moving at 0.5 meters per second. Remember, that's a positive value. It's moving forward. So there's your formula for a velocity and how it relates to a graph of displacement versus time. Now I have another ball. The camera is still taking the pictures once every second. What's different this time? We get to 2 meters in 3 seconds. The ball is clearly moving faster. What's that look like on the graph? We have the same starting point, but we got to the 2 meter mark in 3 seconds. Look at the slope. It's a higher slope because the ball is going faster. I think you can see that it's going 1 meter per second. And that agrees with the spacing on the strobe picture. If the spacing is constant, the velocity is constant. Now, how would we graph the velocity versus time? You're going to have the same time axis, but we have to be careful how we draw the y-axis. That's going to have to be numbered for velocity. It wouldn't make much sense to number the same way on this graph because our velocities are 0.5 and 1 meter per second. Let's plot the slow ball first. It's got 0.5 meters per second here, 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 here. Hey, the slope is the same the whole way. So we can plot that straight across. It's the same velocity for the whole time. How about the fastball? Right from the start, it's going 1 meter per second. At every second along here, it's traveling the same speed. It's all 1 meter per second. Now, why don't I continue that line all the way out to here? I don't have any more data than that. So just to review, the blue is the fastball, higher slope. The red is the slow ball. That's the lower slope. Now, what would happen if we started at a position of 3 meters and the camera revealed this picture? What's the ball doing? Our graph has to start at 3 meters now at time 0. At 1 second, we're at 2.5 meters. This trend continues until we reach 0 meters at 6 seconds. Sure looks like constant velocity, but it's backwards. Using the formula, x final minus x initial, we get -0.5 meters per second. Hey, that agrees with the slope being negative. Now, where do we put it on this graph? We have a problem, don't we? We have to change the way it's numbered. Now we have to account for negative velocities. At every second along this line, we have the same slope. It's all negative. Every second, we have negative 0.5 meters per second. Now we start the ball at negative 2 meters. It moved forward, but something happened to that spacing. Let's see what it looks like on the graph. Something happened when it got to 0 meters. We have two different slopes. We have two different velocities. The ball abruptly slowed down. Putting it on the velocity versus time graph, we have an initial velocity of 1 meter per second. Now don't confuse that with the initial position. Very often kids get the initial position confused with the initial velocity. We're at 1 meter per second up to 2 seconds. Then what happens? We're now at half a meter per second for the rest of the trip. How long did it take to slow down? Well, it's a very short amount of time. It looks like it happened instantaneously, but in reality, we'd just say it's a short amount of time. Could we go from the starting point to the ending point and just draw a straight line? What would that slope represent? That's the average velocity for the whole journey. Calculating the slope is still the same formula. Final position minus initial position over the change in time. And we get 0.67 meters per second. What does that look like over there on that velocity graph? It's actually a little closer to the 0.5 than the 1. Now, why can't I take V1 plus V2 and divide it by 2 the way I would average any couple of numbers? You can see it on the graph. V1 didn't last that long. V2 lasted a lot longer. So it's not a fair comparison to say, well, they both count the same. So the way to do it is to use the change in position over the change in time. This only works if they have equal weight, meaning they existed for the same time.